into discrete values on pixels, but image intensifiers are a continuous, real-time, one-to-one way to amplify light. This is how it works. In a dark scene, limited light from things like stars reflect off the scene and send some photons toward the image intensification tube. The lens focuses these photons onto the tube as an upside-down image, where they go through 3 steps. First, the photon hits a thin plate called a photocathode, made from semiconductors or alkali metals. When a photon hits the plate, an electron in that part of the plate gets excited and is ejected into the vacuum. Next, the electrons are accelerated through the vacuum tube by a voltage. They head straight into another thin plate, called the microchannel plate, and this is made from insulating material, often glass, with about 6 million tiny channels in it. These are all angled at about 5 degrees to get incoming electrons to collide with the channel walls. When they do, they release more electrons from the wall material, which collide even more with the walls, releasing more electrons, creating an electron avalanche. So a few electrons go in, and a flood of thousands come out. Then this flood of electrons leaves each channel and gets accelerated in a straight line by another high voltage to hit a phosphor screen. This is just a screen made of material that glows when exposed to radiation, so it converts the electron kinetic energy back into visible photons for you to see. So every photon that enters the tube gets multiplied thousands of times over while maintaining its position, which makes for a brighter but otherwise identical image. As a last step, there are 20 million optical fibers attached to the phosphor screen that twist the image right side up.
The photocathode, the microchannel plate, that vacuum gap, the phosphorus screen is all in this first section, about the width of my fingernail. The rest of this space is the fiber optic twist.
In the green part of the spectrum. There are 2 types of photoreceptors on your retina, rods and cones. Cones are better for well-lit vision, and they're good at distinguishing color. They're located in the center of your retina. Rods are better for low-light vision, and they're located at the edges of your retina. This is why you can sometimes see dim stars out of the corner of your eye, but they disappear if you look straight at them. The light sensitivity of rods peaks in the blue part of the visible spectrum, so that's why our PVS-31As look like this. They've been upgraded to white phosphor, which looks slightly blue overall, making it easier for people to But the long infrared range is actually emissive, meaning that it doesn't need a light source at all. That's because all objects emit electromagnetic radiation, and the shape of their spectra follows Planck's law. You can see that only extremely hot objects like stars have significant emission in the shorter wavelengths like visible light, but virtually everything emits in the infrared. Because thermal imaging doesn't require any external light like image intensifiers do, and doesn't need to create its own light like active illuminators do, it's undefeated in completely black situations. The entire history of night vision has been driven by trying to minimize these trade-offs. The first night vision technology, known as Gen 0, was developed for sniper scopes during World War II and the Korean War. They used active infrared illumination, much like the commercial night vision goggles of today. Then Gen 1 night vision was developed for the Vietnam War. These used basic image intensifier tubes with just a photocathode and screen, no microchannel plate. They stacked 3 of them together in a row, making them extremely bulky and distorted to look through. But the resulting scopes were sensitive enough to operate just off light from the moon and stars, giving them the nickname Starlight. Gen 2 night vision was developed in the 60s and 70s and added the microchannel plate to the image intensifier tube, increasing sensitivity so that they could be used in dark conditions like on cloudy or moonless nights. This addition also made the tubes much more compact, allowing the first sets of handheld night vision goggles to be created. The last generation, Gen 3, became available in the late 80s. These changed the photocathode material into the semiconductor gallium arsenide in order to better convert photons to electrons. They also coated the microchannel plate with an ion barrier film to increase the life of the tube from 3,000 to 10,000 hours. Though there hasn't been an official new generation of night vision goggles in over 30 years, researchers are constantly working on cameras used in everything from firefighting to building inspections to medical imaging. And the microchannel plate, first developed for night vision, now sits aboard space telescopes like the Chandra X-ray Observatory, helping us discover the hidden world beyond what is simply visible by eye.
Wow. that's beautiful. I'm like, there are like tears in my eyes. Okay, I'm good. I feel like no one can see me because it's in the dark, but you probably can if you have night vision on.